Hello and welcome to the second in my series of OChem lectures. So again, I want to just say where this is coming from. Hopefully after the first two or three, we get used to it. But because the room technology is a little dated, my slides, my presentation does come in cleanly. So I'm going to do all the things I talked about in lecture a second time here so that you see the cleaner view. So this will afford you the choice of seeing the lecture ahead of time. So when you come in for the actual class, you've seen it once, you're more geared up, can ask better questions, engage a little more deeply. The lecture will have obviously the input of student questions that this won't. So it won't be identical to this, but at least give you a good foundation. Give you something to study. I also want to organize these by topic. So for instance, right now I'm going to do, this is the second one in the series. The first one was on the honk rule. This one is going to be on Lewis structures and formal charges. And I want to go slowly so you can review. If it's too slow, you can always watch these videos at 1.5 speed. But I'm hopeful that these are nice, clean, organized lessons. So with that in mind, go ahead and start into this lecture. The sound quality, I hope, is good enough. It sounded okay the first time, but if you have any feedback, please give it to me as soon as you listen to one of these, so I will be able to make adjustments as we go. So, Lewis structures. It kind of picks up on the honk rule where we left off, and that is the honk rule for neutral compounds. Hydrogen will make 1 bond, oxygen will make 2, nitrogen will make 3, and carbon will make 4. So what we're actually drawing, without calling them that at the time in this first sample, was something called a Lewis structure. Lewis structure simply accounts for the presence of electron density around the atoms in a molecule. So we'll go ahead and look at the first of these. So we'll show the conductivity of the atoms with the molecule, and if there are any lone pair of electrons that aren't involved in a bond, we'll represent them by a pair of dots. So for instance, this is a so-called Lewis structure. So breaking it down, this is a lone pair and this is a lone pair, meaning 1, 2 electrons here, 1, 2 electrons here, so that there are 4 electrons around oxygen that are not involved in a bond. And then this line right here represents a bond from oxygen to carbon, and the second line here, the 2 parallel lines, represent a second bond. So we'll call this a double bond between oxygen and carbon. There's 2 electrons per bond. So if we were just to consider oxygen, we would consider it to have 1, 2, 3, 4 of its own electrons plus 1, 2, 3, 4 shared electrons. So it can lay claim to having 8 electrons around its nucleus and its valence shell, which, as you know, is a complete octet. You want 8 electrons. So oxygen, from its perspective, is happy. So let's go ahead and consider carbon. Carbon is involved in a bond to hydrogen. So again, this line represents 2 electrons, 1 from hydrogen, 1 from carbon originally, but 2 being shared. So carbon feels like it gets both because both electrons at any given point could be with a carbon. 2 electrons in this CH bond, 2 electrons in the CO bond, 2 electrons in that CO bond. So altogether, from carbon's perspective, it is getting 2, 4, 6, 8 electrons. So 2, 4, 6, 8. And then lastly, hydrogen, it only provides 1 of the electrons in its bonds, but it can share both. So 2 electrons and 2 electrons. So 2, 2, 8, and 8. So we have the octet rule satisfied for carbon and oxygen. And again, octet rule is pretty much only going to apply to oxygen, nitrogen, and carbon. And the hydrogen is happy that it has its 2 electrons. Okay, so with that in mind, look at a second one. So I want you, that if you're following along with this, to occasionally pause the video. So this is a perfect example. Pause the video and see if you can do the same thing I just did in terms of drawing a circle around what electrons are responsible for, or associated with which atom, and which ones are shared and which ones are isolated lone pairs only associated with one atom. Okay, so we've done that. So when you paused, we have nitrogen with a lone pair, and then 2, 4, 6 electrons it can access through shared. So we have 2, 4, 6, 8 electrons for nitrogen. And we have 2 both bonding, 2 both bonding, and 2 both bonding for hydrogen. So shared electrons, both atoms are laying claim to them because they can be at any given point on either atom. So these are stable structures because they meet the Honk rule. Carbon has 8 electrons, meaning octet stability, and Honk makes 4 bonds for carbon, check. Hydrogen makes 1, 1, 1, 1, 1, so hydrogens are all happy. Oxygen makes 2 bonds, check. Nitrogen makes 3 bonds. So it fits both the Honk rule and this Lewis structure phenomenon. So again, as it states, Lewis structures do not accurately represent the 3-dimensional structure. They don't say where the atoms are, but they just say how they're connected. We're just basically bookkeeping. So this is an accounting trick more than anything. So consider this atom, this molecule, I should say, atom by atom. So carbon, let's consider this first carbon. 8, perfect, we're good. This carbon has 2, 4, 6, 8, 10. Uh-oh, something doesn't seem right there. I must have messed that one up. Get back to it in a second. This carbon has 2, 4, 6, 8. And this last carbon has 2, 4, 6, 8. So something went wrong. This carbon right here has 1, 2, 3, 4, 5 bonds. It violates the Honk rule, which means this is an invalid structure. So somehow, some way, you have to fix that. So I'm going to get rid of last little bit and rid of the yellow part in particular and tell you that it cannot have this. So that bond, I'm going to get rid of that one. And now let's double check to see if this works. I have 2, 4, 6, 8 electrons, 2, 4, 6, 8, all in bonding. So carbon's happy. And just like it was before, carbon had here 8 and had here 8. Okay, one more. Let's see how it goes. So I'm going to do, instead of the electron counting, this time I'm going to do the Honk rule and see if it can still predict my Lewis structures. Carbon makes 1, 2, 3, 4 bonds, check. Carbon makes 1, 2, 3, 4 bonds, check. Nitrogen makes 1, 2, 3, uh-oh, I see 4 bonds here. According to this, it only forms 3. So because this is forming 1, 2, 3, 4 bonds, can't be true. So must fix that. I'm going to fix that by making one less. The lone pair, let's make sure this balances everything out. So nitrogen has 3 bonds as expected. 1, 2, 3. To complete the octet, it has 2, 4, 6 electrons. So it needs a lone pair to make 7 and 8 electrons in its valence shell. So it might be worthwhile for me to go and do this. As size Honk rule, when combined with the octet rule, will be useful in making Lewis structures. Where carbon does make 4 bonds, hydrogen does make 1 bond, nitrogen makes 3 but has 1 lone pair, oxygen makes 2 and has 2 lone pairs. So hopefully this is seeming familiar from what you did in GChem and making sense. The rules are in place. So Lewis structures are things that count for electron cloud, electron density around each atom, including shared electrons. So when you add in the Honk rule that we did before with the octet rule, you're going to be able to draw stable, successful Lewis structures. Let's see if we can do it a little bit more quickly this time. So I want you to double check. And again, shut the video off, try these things, and then click it back on. But for this one, we have carbon making 1, 2, 3, 4 bonds, check. Oxygen making 2 bonds, check. Hydrogen making 1, 1, 1, 1 bond. Oxygen having 2, 4, 6, 8 electrons, valence shell, needs its lone pair. So this one, carbon's a check, oxygen's a check, and hydrogen check, 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 check. Perfect. Okay. Let's see if ammonia is correct. Nitrogen makes 1, 2, 3 bonds. So nitrogen's good because of the lone pair. Each hydrogen make 1 bond. Perfect Lewis structure. Sulfuric acid, a little bit trickier because we're now stepping down a row below carbon, nitrogen, oxygen. So consequently, we now have to consider expanded octets. So sulfur, phosphorus, and then halogens, essential atoms, and oxyacids, they're going to be exceptions to the rule. So we can deal with that emotionally. Let's just make sure carbon, oxygen, nitrogen, and hydrogen fit their appropriate rules. So HONC. Hydrogens all make one bond, check. Oxygen makes 1, 2, 1, 2, 1, 2, and 1, 2. So it's all set. Sulfur just happens to be exception to the rule. So it can have an expanded octet. In this case, can make 1, 2, 3, 4, 5, 6 bonds. Okay, not a big surprise, but sulfur is going to violate some rules. So sometimes it'll only make 2 bonds. Rare occasions make 4, and in some instances it can make as many as 6. O2. This one I bring up not because it's terribly interesting in OChem, but because this is going to be massively important when you take biochem and just bioclasses in general. Oxygen, we think of as having 2 lone pairs in each oxygen, and then 2 bonds. So each one has 8 electrons. But the reality is, it's actually an exception to the rule. So one of the things that you need to make note of is when something's an exception, it's going to be different in a way that is either going to make it more stable or less stable. So in this case, oxygen makes, let's see, 2 electrons here, 3, 4, 5, 6, 7 electrons, and 2, 3, 4, 5, 6, 7. So on each side, there's only 7 electrons that it can count as its own. 7 and 7. And HONC rule, it only makes 1 bond, and we know it's supposed to make 2. So this does not meet either of those stability requirements, meaning this is an unstable molecule. And this is why when you breathe in air, about 75%, just a little under 75% nitrogen, 22, 23, something like that, percent oxygen, depending on where you're at. Of those 2 gases, nitrogen and oxygen make up the vast majority of the air you're breathing in. Nitrogen, you breathe it in, you essentially exhale it. There's a few random reactions it can do, but by and large, it's an inert gas. It doesn't do much with us. Oxygen, on the other hand, absolutely essential critical gas because it reacts with the molecules we have in our body, specifically energy molecules, as we hope, but sometimes other molecules to make, I don't know, messenger molecules like eicosanoids or what we'll learn as prostaglandins. That's a positive thing associated with them. But sometimes it can actually destroy molecules, tissue in your body. So that's the aging process. So whether it's positive or negative, all depends on what it's reacting with, but it is reacting. O2 because of its 7 electron valence shell, or because of its lack of completing the HONC rule. Either way you want to look at it, it is a highly reactive species, which is useful to us, but has to be kept in check. Okay, so let's go ahead and apply this to Lewis structures of all sorts. So I just want to do a quick inventory if this is a good or bad structure we've drawn. So carbon, 1, 2, 3, 4 bonds. Carbon, 1, 2, 3, 4 bonds. So they each have 4 bonds here. This carbon has 3 H's on it, not drawn out, just as a CH3. So I'm going to have to get used to that. This is the first time I'm seeing this, but this represents a C bonded to an H, and an H. So it has 3 H's, so 3 bonds H, and a 4th bond to this alkene carbon, this double bonded carbon here. So in this case, we have all the carbons fitting the rules, and hydrogen, 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 and all 3 of these fitting the rules. This is a good structure. All the carbons have 4 bonds, all the hydrogens have 1 bond. Sounds good. This one, let's do the same double check. H1 bond, H1 bond, H1 bond. CH2, I'm going to assume each H has 1 bond to carbon. This carbon at the end, bond to H, and 2 bonds of carbon. So 1, 2, 3, 4 bonds, good. The CH2, 2 H's, double bond to carbon. So 1, 2 bonds and double bond, 3, 4 with the H's. This one's good. But this carbon right here, bad because it makes 5 bonds. Now 5 bonds to carbon means this structure is not possible. All the hydrogens are good, but that 1 carbon's off. So I'm going to call that a bad structure. And we'll worry about how we can fix it later, but for now it's a bad structure based on that additional bond. Moving on, we have carbons doing different things than we've seen so far. So here we had a double bond popped up earlier, but here we can have a triple bond. Carbon can make a single bond, a double bond, or triple bond. Triple bond means it's sharing 2, 4, 6 electrons. So by either octet rule or the Honk rule, octet wise, this carbon here, 2, 4, 6, 8, because of the triple bond. This carbon here, 2, 4, 6, 8. So they're both fine. Or the Honk rule. Carbon makes 1, 2, 3, 4 bonds here. Carbon makes 1, 2, 3, 4 bonds here. Just double check. This carbon here has 1 bond to carbon and 3 bonds to H's, so 4. This carbon here, 1 bond to that carbon, 1 bond to this carbon, and 2 H's, so 4. This carbon, 1 bond to carbon, 1 bond to carbon, and 2 H's, 4. And last carbon, 3 bonds to H, 1 bond to carbon, 4. So this is a good structure. All the carbons have 4 bonds. All the hydrogens have 1 bond. If you want to draw it out, you're welcome to. So I'll emphasize that the triple bond we start with, connected to this is a carbon with 1, 2, 3 H's. That's why I say this carbon has 1, 2, 3, 4 bonds. This purple carbon here, 1, 2, 3, 4 bonds. We're good. On the other end, so off of the first carbon, it's listed as a CH2. So here's my carbon, H2, so 2 H's, carbon right here, and carbon right here. So let me just emphasize, I made this one purple. I made this one red. The red one also is a CH2, meaning it has 1, 2, 3, 4 bonds. And finally, the last carbon, which I did in blue, H, H, and H. Sorry, that second H is not drawn well. Let me try to fix that. Better. Okay, so this structure, everything is good. Hydrogens all have 1 bond, 1, 1, 1, 1, 1, 1. Carbon is 4, 4, 4, 4, 4, and 4. Everything's good. So it's a good structure. I'm going to erase everything I've drawn so I can make room for new molecules coming in. Let's go ahead and analyze this molecule. So the CH3 with the bond to the triple bond to carbon, same thing, so it's valid in both. The triple bond, carbon with single bond here and 3 bonds here, 4 bonds total. Carbon with single bond here and triple bond here, so 4 bonds total. Just like it was okay here and here, it's okay here and here. So we're good up to this point. CH3s I know we're good when they're single bonded because bond H, H, and H, bond O, so it makes all 4 bonds. CH2, CH3, I know the CH3 at the end has a bond to carbon to keep the chain going, and H, H, and H, so that's good. CH2 on the middle carbon has 2 H's, so 2 bonds to H, has a carbon, so 3, and an O4. So drawing this out, it would look like H3C, C triple bond C, O, connected to a CH2, CH3, and then at the other point up here, carbon with a bond to O and 3 bonds to H. So carbons are fine, all making 4 bonds. Exception here, problem issue we have, that O is part of 3 bonds. Can't be part of 3 bonds and be neutral. So I'm going to consider that a bad structure. So erasing everything I wrote, 3, 2, 1. Not sure why. I'm used to counting down in class. You obviously can pause it or go back as needed. Okay, so oxygen has 3 bonds, can't be possible. Okay, bad structure. See if this is a good structure. I have carbon with 3 H's and a carbon, so 4 bonds. Carbon with 3 H's and a carbon, 4 bonds. This carbon has 1, 2, 3, 4 bonds. Hydrogen is 1. Nitrogen has the right number according to my Honk rule, 3. So all carbons have 4, all hydrogens have 1, nitrogen has 3. It's a good structure. The one thing to make it a Lewis structure, you have to include the lone pair. So that's where the octet rule is a little more specific than the Honk rule. So nitrogen made 3 bonds, but I forgot it also has to have 5 electrons. So 1 of its own, 2 of its own, 3 of its own, and 1, 2 for a lone pair. Or octet rule, it has to have 2, 4, 6, 8, counting bonding electrons around it. And then finally, CH3 is still valid, just like it was over here. H on a carbon. This carbon has 1 bond to carbon, 1 bond to H, 2 bonds N, so 1, 2, 3, 4 bonds. CH3 I know is fine when it's connected just a single atom. So 3 H's, 1 bond each, and a nitrogen. That H is good, that H is good, but where we run into trouble, Honk is not being satisfied. So nitrogen has 4 bonds total. And again, we're going to find how to deal with that down the road. Actually, next slide, basically. But I want to foreshadow and tell you to go back once we do the next page and figure out how I can turn this from a bad structure here into a good structure, bad structure into a good structure. So I'm going to be able to do it by putting some sort of qualification on that molecule. Okay, so formal charges. We're going to introduce this concept. It goes with Lewis structures pretty nicely, but it accounts for when we have an excess of electrons or shortage of electrons from what the atom normally carries. NH4 is going to be one of our easier examples. Every line we're going to represent from 1 electron from each of the atoms. So I'm going to call hydrogen having 1 atom, nitrogen having 1 atom. So those 2 dots, the blue and red, represent electrons. Hydrogen normally has 1 valence electron, check. 1 valence electron, check. 1 valence electron, check. 1 valence electron, check. Hydrogens are fine. Nitrogen, on the other hand, you learned a formula in GChem, and the formula is wonderful, but I'm going to do a visual version of the formula. We're going to consider how many electrons it actually has of its own. Half of the bonding electrons. That's because each bond is made of 2 electrons, 1 from each atom. So the electrons that actually truly are nitrogens came from nitrogen, 1 for each bond. So I draw a circle around the atom and including 1 electron for each of the bonds it's in. Altogether, it's 1, 2, 3, 4 electrons. So it has 4, but normally nitrogen has 5 electrons. It's 1s2, 2s2, 2p6. So the second shell, 2p2, 2s2, 2p3, 5 electrons total. I might have said the electron configuration wrong, so let me go ahead and write this out. Nitrogen would normally be 1s2, which I don't care. It's core, 2s2, 2p6. I definitely did say it wrong, 2p3. So 5 electrons. So normally it has 5, but here it only has 4. So in this case, we know it's a difference of 1. 5 minus 4 is 1. But the question is it 1 too many or 1 too few? And in this case, it actually has 1 too few. So you can think of it one of 2 ways. If it has 1 too few, that means it has one less negative than it needs. So it's going to be positive overall. Or you can just sort of try to add it together. So you can do what it actually has 4 minus what it once has. So 4 minus 5 is a -1. So it's short 1. Math will get you an answer, but won't necessarily help you visualize it. I like the circle approach and just deciding that they differ by 1. It normally has 5, has 4, because it's 1 less negative is 1 more positive. So the overall charge is +1. So let me put that in there. So +1 formal charge for this nitrogen. So let's consider something called formic acid. Again, we'll draw the structure out. This has a carbon in the middle with 2 O's and an H. And so this time I'm going to cheat a little bit. Before, the plus was already written there, so I should have known there'd be a plus kicking in. This one is going to be a negative. In all likelihood, hydrogen is not going to have any of the charges. So we're going to just focus on one of the other atoms having it. Hydrogen normally has 1 electron, check. Carbon has 1, 2, 3, 4, check. Oxygen has 1, 2, 3, 4, 6, check. 1, 2, 3, 4, 5, 6. Ooh, that I have a feeling is going to be my issue. So let's see how it shows up. Carbon normally has 4, actually has 4. 4 minus 4 is 0, or it hasn't been as it should, so no formal charge. Just our oxygen normally has 6, actually has 6, same number, no formal charge. This oxygen down here has 1, 2, 3, 4, 5, 6 plus the 7th from the bond. So it actually has 7, and it normally has 6. So difference of 1. So I know it's going to be a charge of some sort of 1. The fact that it says negative, it's going to be negative. But if you think about it, it has an extra electron. Electrons are negative. So it's going to have a -1 charge. Where these two examples will become important, not necessarily by themselves, but if we put it together, we're going to find things that have an amine and an acid, a carboxylic acid group, amine group. So they call something that has an amine and an acid, an amino acid. So if I combine these two into one molecule, which we will do an example shortly. So CN, I'm going to figure this out, which one has what. So this is where we need to be a little more thoughtful. So the honk ones, the ones I did by honk by knowing the structure of connectivity were easy. Just want to figure out what the connectivity is. So valence electrons will include 4 from the carbon, 5 from the nitrogen, and then 1 extra because of the negative charge. So it'll have 4 plus 5 plus 1 electron for 10 electrons total. So a couple options. It could be made of 1 bond and 4 lone pairs. That would account for 10 electrons total. So a bond is 2 electrons, lone pair is 2 electrons, so 4 times 2 would be 8, plus another 2, 10. So single bond here ends up, from what we know from resonance, this will end up not being a very good structure. So resonance is a topic that will pop up down the road, very, very tested concept. But it comes down to figuring out what is the most stable way to put electrons on an atom. In this case, I have 2, 4, 6 with this. It's lacking the octet. 2, 4, 6, lacking the octet, not going to work. Terrible structure. Okay, so for this one, 2 bonds, 3 lone pairs. Carbon's doing a little bit better. 2 bonds and a lone pair, so 2, 4, 6. Still isn't going to make it. Nitrogen is 2, 4, 6, 8. So I like it better than the previous one. It still won't go. So finally, let's consider 3 bonds, 2 lone pairs. So 3 bonds would be a triple bond, 1, 2, 3. Lone pair on carbon 4, lone pair on nitrogen 4. This one meets the requirements, so check. But now I need to figure out what the charges are. Nitrogen normally has 1, 2, 3, 4, 5 electrons, so this one is fine. Carbon normally has 4 electrons. This one has 1, 2, 3, 4, 5, so 1 extra. So negative charge is going to be on the carbon. Go ahead and put that in there. So actually, let me, instead of drawing that there, let me erase up to there. So there's my negative on the carbon, formal charge. Carbon monoxide, 4 electrons and 6 electrons, so 4 plus 6 is 10. Same story, I could do 1 bonds, 4 lone pairs wouldn't work, 2 bonds, 3 lone pairs wouldn't work, 3 bonds, 2 lone pairs, seems like the best structure. Octet 2, 4, 6, 8, 2, 4, 6, 8. Sounds good. Problem with this one is I have 5 electrons around carbon, 5 electrons around oxygen. Carbon normally has 4, so this has an extra electron, so it's going to be negative. Oxygen normally has 6, 1, 2, 3, 4, 5, so it only has 5 in the structure. So it's short one, so positive, meaning you would get a negative on the carbon and a positive charge on the oxygen. It looks highly unstable. And what we're going to learn in chapter 2 and 3, a little into 2, a little bit at the end of 2, a little bit start at 3. Resonance structures, the compound we draw on with a charge, most stable if you don't have a charge. But if you have to have a charge, you want negative on something that can handle it, a more electronegative atom, and then positive on something that can handle it, a less electronegative or more electropositive atom, if you will. And in this case, plus on an oxygen is bad, carbon with negative is bad, charges in general are bad, but this ends up being the primary structure because if I try to draw anything else that's neutral, I won't meet the octet requirement, meaning I have to have 2, 4, 6, 8 electrons around carbon, 2, 4, 6, 8 around oxygen. So this one's a little bit on the tricky side. I mentioned a little earlier about sulfur, phosphorus being exceptions because they can expand octet, but also mentioned the central atom in a halo acid. So I want to do at least one of those. So if I consider chlorine having 6 bonds, 2, 4, 5, 6. Normally has 7 electrons, so 1, 2, 3, 4, 5, 6, 7. So we're going to be short an electron there. So we're going to have a positive on the Cl. And then O normally has 1, 2, 3, 4, 5, 6 electrons, but here has 1, 2, 3, 4, 5, 6, 7 with that bond. So in this case, it ends up being negative because 7 minus 6 has 1 excess. We already knew that. Excess electron means a negative charge. On the other end over here, chlorine, not the other end, but I guess I should say middle, but to the right of the original atom, it makes 1, 2, 3, 4, 5, 6, 7 bonds or 6 bonds. So it once makes 7, 1, 2, 4, 5, 6. So it only makes 6. It's short 1, so it's going to be short an electron. Gives it a plus charge. So oxyacids generally are a little weird to work with because of this charge distribution. Okay. So I want to toss a question out. C has been eliminated. This is from a problem set that will show up in your life soon. But non-bonding electrons, carbon doesn't have any non-bonding electrons, or it can in certain structures. And so just decide to not cover that, but identify which bonds, if any, carry a non-zero formal charge. Carbon. 4 bonds, 4 electrons, normally has 4, so check. Carbon, 4 bonds, normally has 4, so check. But this carbon right here only makes 3 bonds. So I'm going to call that a positive charge as a result. If it had a lone pair, which it could, in carbanion, then it had 4, it would be tetrahedral shape, it would change its nature slightly. So I just want to go ahead and just leave this as we're seeing it. Okay, the shape around each central atom makes 4 on the green, so-called tetrahedral shape. And then this one here makes 3 bonds, so it ends up 3 can spread out best, and they're trigonal planar. So they all end up going along, each atom ends along a vertice of the central atom, in this case, the central carbon. So trigonal planar with respect to this carbon, that hydrogen, and this carbon all end up at 120 angles in a plane. Okay, so I want to erase what I've written and want to introduce something to stay parallel with the other class, and that is what the book calls, and then what some classes will emphasize, a steric number. Steric number for carbon number 1 is 1, 2, 3, 4. For carbon 3, 1, 2, 3, 4. We already did that. This one only makes 3, so something weird and funky has to happen with that one. Because it's trigonal planar, steric number 3, 3 things around it, those fit. Tetrahedral, steric number 4, 4 things around it, that number fits. So this is a more formal way of doing it, saying it's a steric number, but really it's just our honk count. If we have 4 bonds, we have tetrahedral, 3 bonds, we have trigonal planar or trigonal pyramidal, depending on the presence of a lone pair. 2 will be bent, 1 is just not a shape at all, just a line. Positive in the middle, that becomes key. The formal charge there, the result of having only 1, 2, 3, so only 1, 2, 3 bonding electrons. 1, 2, 3, normally has 4, so 3 and 4 differ by 1. You have a shortage, so you're lacking a negative, which means you balance out by having a positive. This structure over here, again, will have a plus charge here. And trigonal planar will look something like this. Tetrahedral will look something like that. Should have been patient in this, so the computer generated. So formal charges, the last little thing I want to make about this. Mentioned when we did the ammonium and the formic acid groups, that if you have something called an amino acid, so want to revisit what we had 1, 2, 3, 4 bonds to nitrogen before. Those all 4 were for bonded to hydrogen, but now we have a bond to carbon. So it's still going to be the same story. It still has 1, 2, 3, 4 of its own. Normally it has 5, so it's 4 minus 5 or 5 minus 4. Either way, it's difference of 1. Shortage electron means this group is going to be positive. Middle carbon, 1, 2, 3, 4 bonds were set. The end carbon has 1, 2, 3, 4 bonds it's set. This oxygen has lone pair bonding, so 6 electrons set. This one, 1, 2, 3, 4, 5, 6, and 7 because of that bond to carbon right there. So 7 electrons, when it normally has 6, means in excess of 1, so it has a negative. What we've just drawn is something called glycine. It's an amino acid. It's the simplest one to memorize. It is a case of NH3 plus amino group bonded to carbon with a carboxylic acid or a carboxylate group. This is known as glycine. So as it were, this H, you can pick whichever one it is, but that H can be replaced by other things to make different amino acids. So if it's a CH2OH, it's known as serine. CH2SH, it's known as cysteine, and so forth. But that group can vary. So formal charges, quick summary of this. Carbon likes to make 4 bonds. It can form a cation if it's short, so 3 bonds, or it can form an anion, 3 bonds as well, but now with a lone pair. Notice your shapes are different: trigonal planar, trigonal pyramidal. This one's linear, this one ends up being bent. Nitrogen makes 4 bonds or 3 bonds total, so when it makes 4 bonds, 4 single bonds, or 2 single and a double, or 1 single and 3 bonds from that end. So 4 bonds total to nitrogen gives it a positive charge. 2 bonds in the appropriate lone pairs give it a negative. Oxygen, that extra bond, so when it makes 3 bonds, it can only have 1 lone pair, so it's short in electrons, so it's positive. And then when it's OH minus, just basically only thing it does is bind either hydrogen, which I hope you don't run into hydrogen bonded to hydrogen, or H bonded to O. So hopefully this is coming in. I'm adding in extra stuff on that one, but just makes 1 bond, has a negative. We'll pick up geometrical structures next time. I hope this helped. I started to go a little off the rails at the end, but again, if you have questions, ask them during lecture, or hopefully you see in office hours. Thank you very much. I will stop the recording and stop the share.